All right, let's get going. So this is the last lecture of this unit, and we're going to talk about more of the application of things. So we talked about all the cells that are going to be providing us with defense. We talked about the different barriers in place that separate us from the outside world and our environment. So what happens when they fail? All right, these are obviously not the end all be all, but I think these are pretty good examples. So let's talk about when the barrier in question is the genitourinary tract. All right, so common thing is UTIs. And UTIs are typically caused by UPEC, or uropathogenic E. coli. So literally just a E. coli that favors infecting this tract here. All right, just for clarity's sake, down here is the bladder. Oh, that's a little too fat. There we go. Bladder. This is the ureter. Kidneys are up here, not the adult knee. And then down here would be the urethra. All right. So here's the tract altogether, and that's usually what gets infected. The epithelium in question, we didn't talk about it too much. I'm not super concerned with it. It is called transitional epithelium. If you get deeper into this stuff, you'll definitely see that. And sometimes transitional epithelium is called urothelium because it is only found in the urinary tract. So what are some of the defenses that the barrier itself gives? Well, we talked about this. It's pretty logical. Constant urine flow. You urinate a couple times a day. All right? So that is going to flush out any opportunistic rather, invaders that are trying to shoot up the flow. All right? You also have a cool compound called uromodulin, and that's secreted from your kidney tubules, and the cells up here. And what they do is they bind fimbriae, and that prevents adhesion. Okay, so that's a fancy word. So on bacteria, sometimes you'll have a big old tail here, and that's the flagella. And sometimes you'll have little feet. And their little feet are called fimbriae. And that's very helpful in terms of binding to a cellular surface, binding to an epithelium. Having those feet available is really favorable for them. So when you mess with this, it decreases their capacity to lock on. We have a low pH, so our urine is rather acidic, and bacteria tend to not like that unless it is built for breaking down acid, which most aren't. We have secretory IgA, so that was that special antibody secreted by, think about it, B cells. Okay, so those are on your mucosal membranes, also hopefully preventing any adhesion. So those are the innate defenses that we have against an opportunistic pathogen such as uropathogenic E. coli. Okay. So what is the microbe doing? Because if you've had one, they're definitely very common. You know that sometimes that your defenses are going to fail, and there's nothing wrong with that. It just happens. So what's going on? So the adhesion strategy is big here. They use those fimbriae to anchor to the urothelium to overcome that flushing force. So sometimes your maybe the IgA was deficient that day. Maybe the low pH didn't deter them enough for whatever reason. Anchoring occurs. Maybe you weren't going to the bathroom as much that day. I don't know. For whatever reason, the fimbriae were able to anchor. So that's one way. Another cool thing is called invasion. So the bacteria can actually internalize themselves into the wall of the epithelium. So let's see. I'll draw a shoddy epithelium. So this is a row of cells, not a worm. Okay. And then here is a E. coli. What it can do is actually dive into the cell, invade it, and then just hang out inside. So now it can replicate inside, it can form its little own community within, and because it's my cell that it's within, well, now it's evading my innate immune defenses. All right, unless maybe it messes with the cell marker, and then an NK cell uh, can understand that something's wrong. But most of those cells aren't going to know that I have a stowaway in here. So that's a cool thing that these can do. It's called a intracellular bacterial community, sometimes abbreviated as IBC. All right, so yeah, they hide from antibodies and immune cells, so that gives us prolonged persistence, which is not good. Also, you could imagine if these are pathogenic, they are going to release toxins, they're going to damage the epithelium. That's not good. So if we just do a stepwise approach to this, these bacteria will enter and ascend from the urethra up to the bladder. You can be exposed to them from a variety of means. I'm not going to get into that, but let's just say you get exposed, enters from the urethra, go on up into the bladder, and it'll embed in the wall here usually. And then sometimes it can even, like as that infection grows, if the invasion is dense enough, and if we have a lot of IBCs, which are the bacterial communities, well, they build and build and build, and the population's greater, and spread is greater. We get cell lysis of whatever cell that was holding our bacteria, and that causes more and more spread, and more IBCs to form. So you see that a compounding effect. And in that case, we potentially get further ascent from the bladder up to the ureter, and then even into the kidney in some cases. I will say this is definitely like worst case scenario. UTIs are typically not getting this bad. On the I don't know the percentage, but on the 1% that it does, this is very, very bad because your kidneys get a lot of blood. They get a one-fifth of cardiac output. So having a bunch of bacteria near all of that blood is really bad, and you have a high chance of going septic at that point. But like I said, UTIs rarely get up to the kidney level. I forget the term for that. There's a term for that. I'll put it in the comments if I remember. All right, so that's the stepwise there. So we can see how sometimes E. coli can give our immune system the slip. All right, but let's bring it back to the characters, the main characters we discussed here in this unit. Remember the arc that we discussed. So hopefully we have, or actually let me go here. Since this E. coli is pathogenic, it's releasing toxins, so that's going to cause PAMPs to be released. Remember, pathogen-associated compounds. And then hopefully those PAMPs are detected by the PERS. And then those PERS cause the secretion of AMPs. Or we bring more white blood cells, more immune cells. That's the main deal that we want here. All right, so we get AMPs secreted and we get more innate immune cells. So our neutrophils, like you guys said, I looked at a bunch of your cards. They all said the EMT kind of idea behind them, and that's great. They're first responders, rapid migration to the site of infection. In this case, it could cause pyuria, where there's what's the right word? Kind of a white wispiness to the urine. It's not just the regular yellow fluid that it typically is. There's a white wispiness to it, and that's because of a bunch of neutrophils that are trying to combat whatever infection is befalling your urinary tract. So that's pyuria, and that's caused by all those white blood cells trying to fend off whatever's infecting. All right. Your macrophages and dendritic cells, right, they're going to secrete signals to get more white blood cells again in the area. And if they come into contact with E. coli, they are going to act as antigen-presenting cells. So, review. I'll make it red. Okay, so they find E. coli. They don't know that it's E. coli. They just know it's a bacteria from
their phagocytic nature. They're going to eat up stuff and survey their environment. And any damps or PAMPs that are secreted in the area also give them the hint that something is causing us harm. All right, so here's my dendritic cell with all of his arms. And he's going to gobble that up. So that's that phagocytosis. All right, and then after the dendritic cell eats the E. coli, it's going to present little pieces of it on its arms. All right, and then after that, the dendritic cell is going to migrate. And it'll migrate to, think about where it's going to migrate, to a lymph node where our B and T cells are hanging out, with the goal of hopefully finding a B or T cell that is born to fight E. coli. And this could be or T cell. All right, so we want to find that specific response, but again, that adaptive response takes time. So that's what our innate system is doing in this case. All right, and then also exfoliation. So those infected cells hopefully get sloughed off. That's another innate defense we have just from the constant overturning of your epithelium, right? Just like you're overturning your skin cells, your epithelium is constantly being sloughed off. So hopefully that includes any IBC, bacterially infected cells. All right, in terms of your adaptive defense, your B cells, main thing that they do is secreting antibodies. Remember, anytime you see IG, that means immunoglobulin, which means antibody. It's another word for that. Don't stress too much. We'll talk about those next unit. But IgA is the antibody associated with mucosa, so preventing adhesion to the mucosa. And IgG is really good at opsonizing. That's just a fancy word. Bad arrow. Oh my gosh. Let's try that one more time. There we go. For tagging. Opsonize just means tagging a bacteria. So now the whole body knows when some antibody has tagged something, that's just a great marker for the entire body that says, get rid of this. All right. Don't stress too much, but because we'll talk a lot about those next unit. Your T cells, your T helper. T help will sustain recruitment. So with all the chemical signals that they secrete, basically being like the coach of the immune system, telling them what plays to run, what to do, the T helper cells are going to sustain recruitment in that area. And then your cytotoxic T cells will hopefully go find out any intracellular bacterial communities and get rid of them. Okay, so I'll draw a little sword here. Yeah, there we go. So they'll go fight any cells that are infected with bacteria. Oh, that kind of looks like a sperm. There we go. All right, so that's an IBC. Hopefully the cytotoxic T cells find those out and get rid of them. So that's the whole deal there. So basically with an infection, and with all of these, what I'm giving you is sometimes this is happening, sometimes the microbial strategy is winning, or the anatomical context wins and you just don't get infected, or you do get infected for a little bit and then this takes over. All right, so that's kind of the breakdown here. So those are the three potentialities. Either your innate defenses, just the E. coli bounces off, or the E. coli has some strategy to evade, or your immunological cells and concepts that we talked about eventually win out. So it's one of those three things. Or the secret fourth is that this infection goes to your kidneys and something bad happens, but we're not going to worry about that because that's very rare. And that's something you talk about in pathophysiology. All right, so that's a uropathogenic. That's a genitourinary infection. Let's talk about pneumonia. So this is going to be more so um, upper respiratory. Okay, let's spell. There we go. Upper respiratory infection. Okay. Or I guess let's just simplify it to respiratory. Pardon me. Pneumonia usually starts upper respiratory, and then it could be very bad once it goes lower. So I wanted to clarify that. All right. So in the anatomical context of things, right, that's going to be in our trachea, bronchi, and bronchioles. All that means, trachea just means your windpipe. So right here, like your throat, and you can feel like where your Adam's apple is. So that's that respiratory tract. And then as the trachea splits and we go down the different branches of the lungs, we eventually end in like bronchioles, bronchi here, and then bronchioles as we get lower, and then eventually culminating in alveoli. So that's the breakdown of the tree. I'm not concerned with all of that, but if you want it here, so it goes trachea, bronchi, bronchioles, alveoli. It's a little bit of an oversimplification, but that's the branch that we're going down. And if we want to go a little bit more, we can go pharynx, right? So that's where like your mouth and your nasal cavity and all of that area, the back of that uppermost respiratory portion, that can come into play as well. But that's the whole anatomical tract that we have there. Okay? That's your respiratory tract. What we talked about here, we have this pseudostratified epithelium here with cilia hanging off. So that's really important for one of our innate defenses. It's not a cell, right? It's a property of our epithelium. So what uses that cilia? I just write down here, that mucociliary escalator. Really, really important. All right. I will say, as we get down, this fancy epithelium will eventually just become simple squamous. And what I mean by that is just they become flat pancake-looking cells. So they start out, this epithelium here, the PCCE, start out looking like this, and then eventually come down looking like this. And that makes sense because we want these to be involved in gas exchange. That's what my lungs are doing. So we want as little space between this barrier as possible, so that way the molecules don't have to work that hard. All right. The other defenses that we have, yes, we have that mucociliary escalator. Great for cleaning out dust and debris and bacteria. Huge. Also coughing. You don't really think about it, but the whole point of that is to, hopefully huck up whatever is irritating you. That coughing reflex is so we don't get particulate matter in our windpipe, because our body knows that that's bad. Obviously, our innate immune cells, and of course our competing commensals. Any bacteria in the area that you have that have been living in you obviously have not been causing you harm. So if they're taking up space, well, that space is no longer for sale. There's no room for a potentially harmful bacteria such as pneumonia to come on in. So those are our defenses there. Let's talk about the strategy. So a great strategy that pneumonia takes on is residing asymptomatically in the nasopharynx. So nasopharynx, like anatomically, I want you to think, so we have our nose here, right? Let me do this in permanent. So I got my nose, my eye, and my mouth, my lips. It's a really horrible face. But behind the nose, so like if I'm inhaling here, we got my oral cavity here. We have that connection almost, and then our throat goes down. Okay. So through the nose, the back of the nasal cavity, this space right here. So like, I'm going to be a little gross, but if you have some mucus and you kind of like, snort it back and it goes back into that space and you're able to swallow it, well, that is that connection, that pathway right there. That's the nasopharynx. So if pneumonia comes on in, it likes to hang out asymptomatically up here, not cause any trouble, kind of build up its defenses, and then shoot down to cause more trouble. So that's something it can do. Asymptomatically means it's not causing symptoms. It's lying dormant. Another cool thing on pneumonia membranes is something called the polysaccharide capsule. And they just have I guess you can think of it as like a plate of armor on their membranes, making phagocytosis and tagging a little more difficult. What's cool about this is, since we have discovered this, and a lot of bacteria actually use this polysaccharide capsule as a means of evasion, many vaccines are just targeted at polysaccharide capsules, as opposed to like a specific spike protein or a specific part of a bacteria. We kind of take the pamp and damp approach of realizing that, oh, well, a lot of these microbes have this defense, so a lot of vaccines target this concept, which is kind of cool. Yes, so we also have toxin release, poking holes in the epithelium, right? That's not good. That's going to amplify inflammation, more cells, more swelling, more fluid, right? That's a big thing you see with pneumonia is just way too much fluid in an area where we need gas exchange. We need no fluid, and that's one of the things that ends up usually taking the life is that there's so much fluid down there that we can't have proper gas exchange. So the toxin release here is very bad. Then, of course, well, actually, no, not of course. We have our IgA here, yes, of course, but your pneumonia, or hopefully not your pneumonia, if you come into contact with pneumonia, it has the potential to have Ig proteases that can cleave those antibodies that the B cells created. All right, so we hopefully have some IgA on our mucosal surface, but pneumonia has the potential to break that down and prevent it from giving me the defense that this provides. Okay. All right, now to our allies, our innate response. Again, huge. I'll write this again. Definitely know this arc. We have PAMPs. They're detected by PERS. That's a horrible R. Let's try that again. There you go. And that causes the release of antimicrobial compounds. Or we recruit white blood cells. One of the two. Need it. Your complement system can catch up too. So that's, remember, all those different proteins from C1 to C9, and they eventually cause a hole puncher to form that pokes holes in bacteria. So your complement system is really helpful for that stuff too. And then, of course, in your respiratory tree, you have your dust cells. Remember, that's just a fancy word for a macrophage in the alveolus. Alveolar macro. And they also are going to recruit more blood cells. Very, very important. So back to the flooding idea, though. So neutrophils, of course, are EMTs. They're right on the scene. Go to the alveoli, phagocytose, releasing their reactive oxygen species and their nets, but they can increase fluid in the lungs. And that's another thing that I wanted to talk about, and I think I've mentioned it a good bit this unit, is our immune system. We need it to be contextual and graded. All right, so because it's really powerful, and these neutrophils help us out a lot, but if we have too much of them, it is a bad thing. It can cause way too much inflammation, way too much fluid recruitment, and now I'm drowning in my own water,
right? That's really, really terrible. So
I wanted to make that note here.
the point of some of the concepts that I was introducing in this unit is that sometimes we need to tell the immune system to calm down. And that's where like those T regulatory cells come in. That's where our microbiome comes in. That stuff is helpful. That stuff is really important, especially when we start talking about autoimmunity at the end of this class. So hold that in the back of your mind. And of course, if I'm inflamed where I do gas exchange, then I'm going to have bad O2 diffusion. My oxygen is not going to get to where it needs to go. All right, what are my adaptive cells doing? Perfect. My B cells, of course, antibodies, antibodies, antibodies. Secreting those to opsonize, again, fancy word for tag. Whoopsie, there we go, for tag. They'll tag that polysaccharide shell. I already mentioned this. That's the goal of many vaccinations. And again, your T cells, recruiting more white blood cells, the orchestrators getting more of the right players in the right situations, and that causes more amp production. So these guys are helping us out once they get activated, once the innate system recruits the B and T cells that are meant to fight pneumonia. Okay. Lastly, we have one more bacteria that's very annoying, Staphylococcus aureus. In this case, I'm talking about MRSA, which is methicillin. I don't know if I'm spelling this right, just bear with me. Resistant Staph aureus. So MRSA, that is MRSA. I'm sure you've heard of MRSA before. It's a very common bacteria. Real quick, this concept, methicillin resistant. Methicillin is an antibiotic. So this is the idea of the superbug. The superbug. We have taken, or with Western medicine, we've made all these antibiotics and all of these defenses against certain bacteria. But now, folks are prescribed these so often that bacteria have found ways to survive around them. All right? So that's why whenever you're prescribed antibiotics, the doctor says take them all. You must take them all. Because if you don't, if you take like half of it, well then any resilient communities, anything left over is the type of bacteria that was able to resist. So you need to take your entire dosage so you don't form superbugs. But unfortunately, that's already the case. There's a lot of antibiotic resistance bacteria out there because maybe folks aren't doing their prescription to the fullest, or maybe it's being overprescribed. Who knows? But this is a problem that we are dealing with now. So this is one of them, MRSA. That's usually going to infect the skin. So causing abscesses, nasty growths on the skin. So again, the epithelium there was that keratinized, stratified, squamous epithelium. Keratinized, referring to this top layer here that's full of those fibrous protective cells. We have our resident microbiome defending us, right? All of those bacteria that are hopefully secreting some compounds to help us. Our acid mantle, so the low pH, and the sebum oils, all that good stuff. And then our resident immune cells, right? Think about what was the macrophage or the dendritic cell that likes hanging out in the epidermis? Right? Starts with an L. That was the Langerhans. The Langerhans cell. Very helpful. So those guys are our innate defenses and hopefully stop this before it can even get going. But what happens if it does? All right. So the MRSA really likes to colonize nostrils or skin folds is probably better. So like anywhere there's a bend, think of a joint. Maybe like your toe joint, your armpit. It's very common in the armpit. just that tight region that maybe you might miss while washing, something like that.
So adhesion is going to bind the host's epithelium. It's pretty good at antibody avoidance just because of how its membrane is set up. Don't worry too much about that. It likes to secrete toxins that perforate the local tissue. So all of those stuff, right, that's going to secrete damps and PAMPs. Okay. Let's go with that. Damps and PAMP release because of that. A really cool thing that it does is it forms a biofilm. This is what I'm mostly concerned about with MRSA. So this is structured community of microorganisms embedded in a self-produced slime matrix. So that's all this is. It's a slime matrix produced by these bacteria. And what this does is it increases longevity, colony formation, and antibiotic resistance. And this is what leads to the abscesses or the growths characteristic with MRSA. Okay?
So think about that. When I talked about mucus, I talked about how helpful it is, how your body uses that as one of its go-to defenses. So this isn't necessarily mucus, but it's a slimy matrix that the bacteria secretes. So it's very similar. The bacteria is like, okay, if you use mucus, I'll use my own. And it works very well at increasing longevity, colony formation, and antibiotic resistance in the same way. We have it, or it hides in this matrix. So if our antibodies are trying to get rid of it, if our white blood cells are trying to get rid of it, well, it gets stuck in this mucus, and it can't operate to the level of effectiveness that it would normally.
All right.
So your innate defenses, yes, we have our keratinocytes that'll secrete AMPs, hopefully stopping this, but in response to stress, i.e. your DAMPs, right? Your complement system hopefully coming in to poke holes in these bacteria, and your neutrophils coming in to secrete, to drop their nets, and your macrophages coming in to do some phagocytosis and some antigen presentation. Okay, so if you'll notice, like, it's a very conserved response. Like, this is what they do each time. The neutrophils are going to do neutrophil things. Their macrophages are going to do macrophage things. And then for the adaptive response, like, yes, it's specific, but it's still conserved. They still do the same thing. The B cell meant to fight, in this case, MRSA, is going to get activated by your antigen-presenting cells. And now I'm secreting antibodies. Now, because MRSA has like a weird membrane, it's not the best for tagging, but it is still useful. And then the same thing here with the T cell. That's meant to fight MRSA. That one gets activated by your innate system, and now we recruit and activate white blood cells that are going to be most helpful in getting rid of this infection. Okay? So, those are the 3 pathogens we're talking about this unit. Okay? So, all I was worried about is applying the cells, applying the concepts we talked about, and then showing you a couple ways that bacteria like to employ strategies to evade. There's a couple ways to trick our immune system, but hopefully for a short amount of time. And then the other immune properties we talk about hopefully kick into gear, especially if you aid that with some medicine or some antibiotics. All right, so that's what I wanted to go over today. I hope that wasn't too overwhelming. Thank you guys very much for your attention.